isomorphism of between homology and its modified version, where we require all chains to be sitting inside particular patches of some cover, some topological space. And so we continue this proof. So we introduce linear chains, space is a group of linear chains which we can understand as a free group generated by ordered points in Euclidean space Rn, and we define the map, we define the boundary homomorphism. Just essentially by the formula similar to what we had before, and it shows that it satisfies this relation. So now we want to define some other homomorphisms on this between the spaces. So in particular, we want to define the following thing. So let me fix some point B in Rn, and then for the fixed point, I want to define a homomorphism from LCN to LCN plus 1. And so this is generated by these sequences points in Rn plus 1. And what I do, I just add, in the beginning, I add this point B at my fixed point P. Okay. So what is it, so how do I generally understand this? So if, for example, if n equals 0, so I start with some point, kind of zero simplex in Euclidean space, and so and there's some sort of point B here. So what it goes to one simplex with n points V0 and B. And when n equals 1, so I start with this thing. So this is some one simplex. So here I remind you that this is probably so this is the points. I probably in principle the simplex can be degenerate because this is defined as a linear. So one option to define the linear maps in R. So in principle, these 2 points can coincide. And the more generic situation looks something like this, and we have so we have this extra point B, and so we get some element in LC2. So yeah, in LC2, which should be this kind of triangle. Okay, so now we want to show the following property. Between a composition of this homomorphism and D, which we had before. So let's see. So again, let us say consider left hand side and act it on some arbitrary generator. And okay, so I just use the definition of phi b. So I add a point here. And then I by D, so D I have to take a sum. So I have to remove points one by one here, and this plus minus signs. So it will be look like this. The first term will be V0, V1 till Vn. It will be minus B, so I remove second point minus B, V1 till Vn, plus B, V1. sorry, yeah, V0, V2, dot, and so on. And I can see that I can separate my the first term. So the first term I can send just identity acting on this generator which we started with. And you see all other terms, they look, they have B in front of them. And so these all other terms, they can be sort of B as this phi B acting on V1 phi B, V1 dot Vn minus V0 V2 dot plus dot, and of course this is the same as D acting my original generator. So indeed we showed this. Okay. Questions? Okay, so now we want to introduce the following notion, which you're probably familiar with. So lambda. So consider some linear singular simplex in impedance space, and so I want to define a particular point in Rn associated to this element, to this sequence of points. So I define it by taking the following sum, for each the I. So if I understand there's an element in this Rn as a vector space, I can divide it by n plus 1 and take a sum over all vertices here. So this gives me still Rn. And speak again as sort of the barycenter of lambda. So for example, if lambda, so how does it look? If lambda is just a single point, then D is just the same point. I start with a point B. And so if lambda is a pair of points, 0, V1, so B is just is the middle of this interval. And if lambda is a triangle, again possibly degenerate, V0, V1, V2, how we define the barycenter. So we take a intersection of medians and this, and this will be my B lambda. B lambda here. Okay. You can set the center of mass if all these guys have the same mass. Okay, so now we want to consider what is called barycentric subdivision of lambda. So what does this mean? So I start with some lambda, generator of this form, linear linear simplex. So we want to define this recursively. So the formula which I read should be answered recursively. So I understand this as a union of the following simplices, such that so if I remove b lambda from here, so b lambda is the barycenter of lambda, and if I remove this guy, so the rest, so this n some n-1 simplex is inside, this guy should be inside barycentric subdivision of face of lambda. So I start with lambda. Why this well-defined procedure? So if I start with lambda, so I define how to so there's some n simplex, and so I do this. So suppose I already know how to do this barycentric subdivision for n-1 simplices. Then I know what this means, because the faces of lambda are n-1 simplices. So I can understand what are those guys. So I can understand what are these guys. So this will be subdivision in terms of simplices which have non-intersecting interiors. So again, let me give you examples so to be clear what's going on. So what happens when n equals 0? So n equals 0, this is does nothing. So this is just the point is subdivided into a point. And so for n equals 1, so I start with some interval v0, v1, and I consider this union of this form. So I can start just, so this will be my b lambda, and so this guy, so here there will be just one w here, and this w, this single w should be inside the barycentric subdivision of a face of lambda. So the face of lambda here are just points, and we know this barycentric so this guy is just this point to this point. So this means that this is a union. This is b0. Sorry, it should be this b lambda b0 union b lambda b1. So what this means, I start with this simplex and I subdivide into two smaller simplices by dividing them in the middle of the interval. Okay, so what happens when n equals 2? I should start now with some triangle. And okay, so see my barycenter here. So however, if I apply this recursively, so it should be so suppose I should consider this the sum over of this n-1 simplices which are inside barycentric subdivision of faces of lambda. So the faces of lambda here are just, well, this is this interval, and this interval. So for integrals, we already know how to do paracentric subdivision. So we just split it into two halves. So we have to, this sum will be over 6 intervals like this, right? And so there will be, so if I, for example, denote this, I don't know, W0, W2, well, my choosing different U0, U1, and U2. So, for example, in particular, there will be B lambda, and then I repeat it like this. So it will be B lambda U2 U0 union B lambda. So for this guy, lambda U2 U1 and so on. So it will be 6 small elements. So this is the first. And in general, so this is applicable in general. In general, you have something of this form. Just by dividing this recursively. Questions? Okay. So now I want using this notion of barycentric subdivision and notion of barycenter. Let me define the following another homomorphism from LCM to LCM, and any element here will be taken to the following. So what does this mean? This means this defines recursive. This is a recursive definition. Why this is okay? Because so suppose I know how. So this is lambda in LCN. Suppose I already know how to act on lambdas from LCN minus 1. Then I calculate the action on lambda from LCN because d of lambda is something in LC and minus 1. So if I know how S acts on LCN minus 1, I know how it acts on LCN. But of course, I need to define the starting point. So I need to define what was going for n equals minus 1. So this is not to use recursion. So for n minus 1, the only element is the empty sequence, and I define it by acting as identity. So for again, let me write examples. So n equals 0. So the elements, the generators in LC0 looks like this, just sequences with one vertex. And so I want to use this recursive definition, so I do like this. So now I need to take a d of this, and d of this, as we agreed, will be empty sequence. And this we already know how to calculate. So this is given, and this will be 5b lambda of empty guy, and this is just b. Well, b lambda we know in this case it's just the V0 itself, right? This is V0. So here you see for n equals 0 it also acts as identity. And this is all. And so we have n equals 1, S, we start with some interval, and so this will be lambda will be in the middle of the interval. And so doing a recursive definition, so I should I use this formula, so d, so now I put d of this, so d of this is d1 minus d0. And so now I already know how S acts on one simplices, and sorry, zero simplices, and so this will be this we know that this acts just as a negative. So this will be phi b lambda on b1 minus b0, and this is the same as b lambda b1 minus b lambda b0. So what I get, so I started with an interval, and the result was this interval minus this interval, for each halves. And you can check the similar so n equals 2, I leave you as an exercise. But you can check that the result will be the sum of plus minus lambda I, where I comes so from 1 to 6, and lambda i's are in barycentric subdivision of lambda. If I start with lambda like this, I do barycentric subdivision. So the result of application of S will be sum of this. So start with this big triangle, and the result of S will be a linear combination of these 6 small triangles, with coefficients being plus or minus 1. And this is true in general. So in general, S lambda is a sum of plus minus I lambda I, such that lambda I are in barycentric subdivision of lambda. Questions? So this S operator divides your simplices into smaller simplices according to this barycentric subdivision. But the result, with particular weights plus or minus 1. And the signs are fixed by this explicit formula. Okay, so okay, similar to this operator phi, we want to check the following property for S. So we want to check that S commutes with D, so S is a chain mode. So since S is recursively defined, so it's natural to prove this recursively. So by induction. So first let us check the base. The base for n equals 0. So this is we understand this is as equality between homomorphism from LC(n) to LC(n minus 1). Okay, so n equals 0. we know that, so let's check, so for n equals 0, we start with some generator, v0, just a single vertex, and so S, we know that acts as identity in this case, and D gives me an empty sequence. If I do it the other way around, so this would be S, then acting on empty, and this is also same as empty. Okay, so the base of induction is checked. Another step, we do the following. So, so I take lambda, some element here, and act on it by this homomorphism. And let's see. So, so I use this recursive definition over there. So this would be d phi d lambda s d lambda. Okay. And then, so I showed the following. I showed a certain property for this homomorphism phi d lambda, so we can use it. So we can use it. This is this part is the same as identity minus phi d lambda d. So they had a equality already shown. This is constant. And okay, then so what I can do, so okay, let's multiply. So this will be the same as d lambda minus phi d lambda ds d lambda. So now this is guy in LC n minus 1. So I can use my induction assumption. So I already know that this is equality is true on LC n minus 1. So I can use it. This is S d lambda minus phi d lambda S d lambda. And this is equals 0. And so the whole thing equals to 0. Check this property. Okay, good. So we also need one more homomorphism from LCN to LCN plus 1. And we also will define it recursively by the following from lambda minus lambda. So again, since this is in LCN minus 1, this will, so this gives me a recursive definition. Well, of course, again, I need to define my initial condition. When n equals minus 1, I define t on empty space. Okay. This defines recursive. And for t, I want to check the following property. So this is a property between homomorphisms from LCM to LCM. Again, we'll do it by induction. Okay, so base n equals -1. Well, t equals 0. We know that t acts t is 0, d is 0, and we know that s LC -1 is identity. So this is just 0, and this is also 0. So the base is fine. And now the step, induction step, is the following. So let me start with this guy and act it on some element lambda from this group. So this will be, and use this recursive definition. So again, I will use, for this combination, I will use my identity on phi, which we had before. So this is the same as identity minus phi v lambda d. So I replaced this composition. And let me just use this unchanged. And let me just apply this combination. So let me apply identity on this. So it will be lambda minus t d lambda and minus phi d lambda d lambda minus dt d lambda. Okay. And I want to use, so again, so this is in LC n -1, so I can use my induction assumption. So dt, I can use this formula. I assume this formula is already proved for LC n -1. And okay, so I keep it first. So I keep this unchanged. But for this part dt, I use this formula, so it will be minus identity minus s minus td acting on d lambda. Right? Okay, now I can simplify this. Okay, lambda minus t d lambda minus phi d lambda okay, fine. And well, actually, yeah. So this is the same. This, and then it will be plus phi d lambda z lambda. This is just identity. So this is the cancels out. And so this last term will be 0 because the decomposition with d with d is 0. And then we have minus phi lambda, sorry, minus plus, sorry, minus phi lambda s d lambda. So I think I missed something. So I missed No, I think it's sorry. Wait. Yeah, okay, yeah, it's good. Everything is good. So. Yeah. Continue here. So okay, so in the last term I use it. The fact that I can. Well, S. We know that S can be commuted with D. So continue this lambda minus T lambda. Minus. So ds. So yeah, commute S with D, and then I notice that this is a recursive definition of S. So I get what I wanted to show. This is lambda minus T minus S. I get it. So to summarize, we defined operators, the following operators on LC, well, with some index T, D, S, and phi B, and we showed they satisfy a bunch of relations like this. Okay, so now we want to define the analogs. So now I'll come back to our chain, to our singular chains in some topological space X. We want to define analogs for those operators on C of X. And to do this, we noticed the following. So the elements here, the generators here. Our singular simplices like this, but I can understand this delta M itself as realized as a nonlinear chain in Rm if M is greater than M, right? Particular example. Here we have conditions. This is a non-degenerate simplex, but particular type of linear chains. You can always realize the standard simplex as inside plus one by linear map. And then if you write formula of this form, sigma restricted to the following linear combination where delta INs are n simplices inside delta n. So they're not necessarily faces, but they're just some, well, they're not faces, but there's just some sub-simplices in delta n. So what this means, this notation, this means by definition, this means that I take the sum of sigma of this sigma which we had before restricted to this simplices. So the restriction is well defined because this is inside this guy, and I weighted with this m which we had here. So we assume that this guy is an integers. So this defines me an element. This is a well-defined element in Cn of x. Integers. These are integers, and these are some singular simplices. So in particular, the example of the use of this notation is that if you write some sigma restricted on delta of n, and here we understand delta as acting on linear chains in Rn. This is, and if you use this definition of this notation, then it's the same as our previous definition of delta, right? Because it's exactly the sum like this. So more explicitly, on the right, this is because this is the following delta I n minus 1, which faces so in general, this is maybe this n may be different. Even the same. So now using this approach, we can extend all our operators to operators acting on Cn of x. So for example, S, now we can define Cn of x by taking singular chain here. So the singular chain here is understood as a delta, is a mark from delta n to x, and considering its restriction on S of delta n, and this we know, this is the sum of the following form, sum of plus minus is lambda I, where lambda i's are in barycentric subdivision of delta n. And this is, by convention, is the same as plus minus sum of I sigma restricted to this number. For n equals 2, we start with some sort of triangle. You do barycentric subdivision into 6 small triangles, and the result is the restriction of this original sigma mark to the small triangles with plus minus signs. In particular, automatically all the identities will hold before. So, for example, why this is true? Now it's considered as a policy in the homomorphisms from Cn of x minus Cn minus 1 of x. So, okay, if you act on the left hand side on some generator, this is the same as by definition, the same as d sigma s restricted on s on delta n. So if I first act by s on sigma, but then d I can understand as always as sigma restricted to d acting on delta n. And for this, here we already can use this property, because this here we have just linear chain, and so this is the same as d delta n, and then we just repeat it in reverse. So this is the same as S sigma restricted d delta n. This is the same as S. Sorry, S. This is the same as d sigma. Well, this is just original sigma. Yes. And similarly for all other identities. Similarly, so t plus t equals minus s. Now this is the identity, the homomorphism from Cn of x to Cn. Okay. Questions? Okay, so now let me define the following iterator dm. It's following sum of compositions. So this is, will be a homomorphism from Cn of x to Cn plus 1 of x. S doesn't change in index, and t shifts the index by 1. Okay. So, and we want to check the following. So let's see what happens if I consider the following combination of homomorphisms. So this is just using the definition of this dm. So this will be the sum and now I can use the fact that the d commutes with s, so I can commute it all the way here. I get the following. Right. And then I can use the formula for this. And this will be so now I see if I open the parentheses, so almost everything in two sums cancel out, right? Except the first term and the last term. The first term, the first term here in this part, which is identity, and the last term here, which is S n. So what does it mean? So we already saw what is the geometric meaning of S. So S divides simplex or smaller meaning that it takes a simplex and gives me a linear combinations of small simplices which appear in bicentric subdivision. So if I apply it multiple times, this the subdivision will be finer and finer. So when I start with some triangle, I do S once, so it gives me a linear combination of these 6 smaller triangles. If I apply one more, this gives me. So I need to subdivide every one of them. Like this. And so on. So this is S squared, this is S3, and so on. So if I take high enough power of S, this subdivides my simplices into very small ones. So I understand this. So this is so I can consider it as a single simplicity inside my X. So if I X head somewhere like this, and suppose it's covered. So I have the cover of this X. Suppose it looks like this. This is U1. U2, U is color. Start with this. So you see, if I can start with some simplex, and it's not going to be inside any particular U. But if I subdivide it enough, I can make sure that the small simplices are always inside a particular UI. So this is the idea. But yeah, I'm not well, one has to be more precise, more careful, and do some sort of analysis, which I'm going to meet. But the idea is like this, so that and the point is the following: so that for any sigma, for any singular simplex in X, there exists M depending on sigma, so some integer number large enough such that S to this power acting on sigma will be inside our modified chain complex X, which is a subgroup Cn of X. Here I remind you, so this is a group, a Fairbairn group generated by singular chains whose image is completely inside one of the subsets in this cover. So by taking M large enough, I can always sure that. So we know that this is this has the following form: is that this is a plus minus lambda I, where lambda i's are in in a subdivision of sigma obtained by applying bicentric subdivision M sigma times. I can always make it small enough. To be precise. No lambda I. Of course, if you kind of make this, subdivide this guy as delta m for the small guys. I mean, the images by continuity, the images will also be small enough, so we'll always can constrain the images to also be inside these UIs, inside the subsets. So then we can define the following D, which is the homogeneity from Cn of x to Cn plus 1 of x, and it will send sigma. So before we defined D with one particular index m, and now we just use D with this m of sigma, which we chose here. It's taken large enough so that this is satisfied. Okay, so and now I want to take row. So one idea. So what do we want to show? So this is we have some inclusion of chain complexes. So we announced that we want to show that this inclusion, the induced mark on the corresponding homologies, actually will be isomorphic. So what we want to do, we want to find homotopy inverse, or chain homotopy inverse to this I, this chain mark I, and we are going to use the following candidate for it. So let me just define it like this. And this is a map from Cn of x to Cn of x. And first we want to check that this is a chain map. We want to check this property. Which all commutes with D. Okay, just use the definition. So let me act on some generator. So this will be this is the definition. This will be D of sigma minus d big D and minus d sorry d sigma and so then okay, this is 0, and if I act the other way around for d from sigma. So again, use the definitions of this d of sigma minus d sigma minus d sigma. And now this term is 0, so we see that these are the same. Okay, so this is sorry, we checked this. So this means that R is a chain map. Well, we also want to show that the image of ρ is inside this modified chain, single chain complex Cn of x, which is a particular subgroup in Cn of x. So let me act on some sigma, some generator. So this is sigma this is sigma minus d. Well, d. Now I can use explicit formula for this big D. We know that for particular sigma we need to replace the d by dm of sigma minus well, this is, let us see it like this. And so now let me, so we showed the following identity on this combination. So we showed that this combination can be replaced by identity minus s to this power minus dm sigma d sigma. Okay. And well, again, this cancels out, so what is left is s sigma plus dm sigma minus minus d acting on d sigma. Okay, so well, this we know by we argued that this is inside this subgroup. We can take by choosing this particular large. What about this guy? So so this can be the second term can be understood as follows. So so d sigma has the following form. So the sum of plus minus 1 of sigma I, where sigma I is restriction of sigma on a face. Okay, and then so by linearity, this is a sum. The same sum which appears as the definition of d of d m sigma minus d acting on sigma I. Well, d acting on sigma I, if I have to replace it by m of sigma I, dm sigma I. This. D and sigma I. And this difference acting on sigma I. Where sigma I are restrictions of sigma on the faces. Okay. And, okay, so let me start. So let's analyze it separately. So this is if I use the definition, so remind you that the dm by definition was this sum, right? Okay, so if I act with this difference, it will be the following sum. Take I sigma j. The sum will be all i's, which is a difference between index here and index here. Okay, I need to choose a different index here. J. It should be different. J. Sigma j. Sigma I. Okay, and well, you can see that this is so each of these guys, because this power is larger than this is inside Cu and X, and And we also know that well, this subgroup is preserved by the action of T. This is inside. Right, because well, this action, the T acts just by doing, well, if you look at the definition of T, which was well, defined as adding some barycenter and so on, it doesn't change. It doesn't. The definition of T, it takes me some singular simplexing, gives you some linear combination of other singular simplex, which are essentially restrictions on subsimplices. So of course it doesn't modify. So if the original simplex was inside one of the, its image was inside one of the subsets in this cover, the result was also be, the resulting simplex is also be with image inside those subsets. So in particular, by summarizing this, we learned that the rho of sigma is inside X. Okay, and so it follows. So rho was originally defined as the homomorphism from this group to itself, but since its image is inside this subgroup, we can consider rho can be considered as a homomorphism from Cn of X to this group. And I was this inclusion. So I is just inclusion. So now what we want to check is this pair of maps, they are chain homotopy inverse features. And then it will follow that I isomorphism. So, well, by construction, we have this property. By construction of the rho operator. I mean, it was without composition with inclusion, but since we have this property, then we can replace it by composition with inclusion. Nothing changed. So we have this, and we also have rho. The composition the other way around is just identity. Why is that? So this is because if we start with some sigma in Cu and of X, so somewhere in the image of this inclusion, then it can take M of sigma to be. So we don't need to first subdivide the sigma. So we can just take M of sigma for such sigma to be 0. And then this D acting on sigma will be just 0. And therefore, if I start, so I start with this formula, rho d plus dd. And so if I restrict it, so this was here, the rho was understood as a map from this space to itself. So if we restrict it to elements in the image, so if I compose in the image of this inclusion, so if I compose with inclusion, this everything here will be 0, and this will be just a limit. So now, so we saw that we see that this well, this map is just identity. So this from this we just know that the corresponding induced maps. They should be giving me some just identity on the corresponding homology, which is here. This is our modified homology. Because this is this equality on the homomorphism from this space to itself, and well, also the other way around. So this is D plays a role of chain homotopy between this map and this map, so which we already know in general that this implies that the induced maps will be just the same. This will be identity on the chain of X. And this means that I start is an isomorphism. This is a proof of the lemma. Okay, so now we can relatively easily prove excision theorem. Which we already announced. So we will prove reaction to. Okay, so version 2, let X be a union of interior of subspace A and subspace B. And let me, so I can use then this A and B to be my, to realize my color. Okay, so A and B, subspace X. And so in this formula, which we already proved in the lemma, so in this formula, all maps take Cn of A to Cn of A. Because already, so here, if you take some because this is already A is one of the subspace with the color. In particular, if you take some singular chain here, we don't need to first subdivide it. Therefore, they define induced maps on the quotient. So on the quotient, so if you start with some group and divide it by Cn of A. what this means, this means that if I consider this modified chain complex of X and divided by Cn of A, so this guy had a map. There was I took it to Cn of X, and rho was a map back. So we can just define. Now we divide both sides by Cn of A. And so this we can notice that this is the same as Cn of B divided by Cn of A intersected with B. So why is that? Because what is the meaning of the numerator here? So numerator here are chains which with image either measure of simplicity with image either in B, completely in A, or completely in B. And we divide them by chains with the image in A. But so this can be understood as chains. In particular, all chains in A here, they will be factored out. And so we only have to worry about chain in the numerator. We only now have to, because we divide by this, we only have to worry about chains in B. And we consider the modular chains, which also falls completely in A. But this is the same as so it's in B, but also we want to model chains in A, which are also in B. So it's the same as factoring out chains which are in image both in A and B. So in the section. Okay. And so we still, on these induced maps of the quotient, we still have this formula. So we still have the property that the induced maps on the homologies of these chain complexes corresponding to the quotients, they will be inverse to each other. So this means that, in particular, this means that Hn, the homology associated to this chain complex, is isomorphic to the homology of this chain complex. And this is, by definition, the relative homology. This is because, in particular, I, so induced, this is I star, this is and they are inverse to each other. Okay, let me, this actually will be needed for for the exercise. So let me reduce the following definition: reduced homology. Well, this is actually not it's a relatively simple notion, but reduced homology. So consider what is called augmented chain complex. It's a small modification of the original chain complex. So the beginning is as before, but at the end, what we want to add, so we already considered actually this extension before. We want to extend it by this map epsilon, so not 0 but epsilon, where a linear combination of singular chains in C0 is sent just to the sum of i's, sum of the coefficients. So we have this when we consider it homology of a point, I think. And so for this, so this is also a chain complex, and we can define the corresponding homology. It is called reduced singular homology, and it's denoted by h and tilde of x. So now it only modifies the homology group at 0, right? So actually it's the same. So it's the same as the usual homology for n greater than 0, and for 0 this is the same as h0 of x divided by z. So this is already so it's the same as this example of homology for point. Because the kernel, so in 0 place, so what is this? This is the kernel of this map divided by the image of this map. And but before we had this map was 0. So and the kernel, so the image is actually the whole space, and the original homology was just the same as well, okay, let me elaborate on this maybe. So h0 tilde of x. What is this? This is the kernel of epsilon divided by the image of delta 1. So the kernel of epsilon is C0 of x divided by z. And this is d1, and this is the C0 of x was the same as kernel of d0, which was previously. So before we had d0, we just send it to 0. So this is the same as h0 of x. And particularly if x, so we know that if this is h0 of x is just direct sum of copies of z corresponding to fast connected components. And this quotient can be understood as diagonal z. So in particular, so if I take the reduced homology of a point, this will be 0. Because non-reduced is just, well, 20. No, it's just 20. Non-reduced was 0 except when n equals 0, but now when n equals 0 it was z. Now we divide it by z, so it's just 0. So in general, the reduced homology of x is actually is isomorphic to homology of x relative some point inside of X, but this isomorphism is not canonical. Well, if X has several past-connected components, the isomorphism is not canonical. Okay, so now I want to, yeah, sorry, I will go over time a little bit, but I want to finish. Well, they're not going to be any technical theorems as a slammer. So you want to use what we showed before to show another theorem, which will be important. So it kind of allows to calculate homology group in various. So suppose this is A is some subset in X which is non-empty, and suppose there exists neighborhood V of A such that this neighborhood deformation retracts to A itself. And so such pair of topological spaces X and A is called good. Okay, then the quotient Q so this is the topological quotient where we identify elements in A. So we collapse A to a point. So the equivalence relation of point belongs to A takes the equivalent if the point belongs to A is the equivalent. And so of course this is the quotient, it's just a point. It's a unique equivalence class. Okay. And so this quotient induces isomorphism Q star X. And this is, you know, since this is just a point inside this space, this is just isomorphic, again, non-canonically to the reduced homology. So what is the proof? So we use the result for long exact sequence for a pair of topological spaces. So we can see the long exact sequence for a pair V and A. V is our neighborhood, which satisfies this condition. So it looks like this. HM A I star HM V HM V from A. This is a long exact sequence, which we already know about. And so on. So this is this were inclusion maps, and this was our delta map. And this was a quotient, well, not quotient, only quotient for this relative chains. And so we know that V deformation retracts to A. And this means, so this is a chain homotopy equivalence. This means that the inclusion, we know that if V deformation attacks to A, the inclusion of chain is is a homotopy equivalence, and therefore the induced map is isomorph. So those are isomorphisms, and this means that in particular this map should be trivial, and this map is also should be trivial. Because if this map is surjective, so the kernel of this map should be the whole space. This is trivial. And similarly, this map is injective, so the image should be trivial. So this map is 0, and it follows that then this is should be 0, right? So in the log exact sequence, if you have some group sandwiched between trivial maps, it is necessarily 0, right? Okay, and okay, so we learned that these relative homologies are just 0. And okay, so then let me consider the following short exact sequence of chain complexes. The short exact sequence of chain complexes for the pair of X and a subspace V. And so one can quotient everything here with respect to Cn of A, because this is a chains with image in A, there are subgroups here, here, and here. And so how this modifies our things. So this is gives me the Cn of E divided by Cn of A. And this is the Cn of X divided by Cn of A. And this is actually is not modified because this is A is inside V, so Cn of A is a subgroup here, but I already quotient it over this larger subgroup, so it actually doesn't do anything anymore. This is inside. Okay, and so I have this short, and I can understand. So I have a short exact sequence of these chain complexes, and by the general theorem, I can there will be induced a long exact sequence of the corresponding homologies, which will look like this. So the homology of this quotient of this chain complex, which is a quotient, is relative homology V, A, and H and X, A, H and X, E, and then I go next line, Hn minus 1, B, A, and so on. This is should be very familiar with. So before we showed that these are trivial groups, right? So I showed that all these groups are trivial. So in particular, this is map is trivial, this is trivial, and therefore this must be an isomorphism. As we know, if a pair of in the exact sequence, if a pair of groups is sandwiched between trivial maps, this is necessarily isomorphic. This is isomorphism. And okay. And another thing is that well, we know by the condition of the theorem, we know that this V, which is a subspace in X, deformation retracts to A. So if I quotient, we consider quotient respect topological quotient respect to subspace A. This V quotient by A will be a neighborhood here of this is neighborhood of A divided by A, which is a point, and this deformation retracts to this point. Before, because this deformation retracts to A. And so we can repeat previous argument repeat the previous argument to the quotients, because we have a similar situation, and learn that. So we repeat this argument for the quotient, and we learn that we also have this for the quotients. There is a corresponding isomorphism, which we call G star. So x divided by A, B divided by okay. Okay, so we're almost done. Okay, so let me just draw the following diagram. So this is the induced, so Q stars will be in this diagram are push forwards of the quotient maps. So the quotients respect to, or if there's some topological space, I can say there's a quotient map of the space, or this either X or some subspace in X divided by quotient by A. And so particularly we have this, and we also can consider pair XB, and here is the quotient. We will send X to X divided by A and V divided by A, and there will be a third column Hn of X minus A, B minus A, Hn X minus so now I consider the following: Hn X. Consider X minus a complement of A in X and complement of A in V. And I also can consider the quotient of it.
What is the meaning of this minus?
Well, minus is a complement. But I mean, actually, this is this quotient is just well, it's divided like this, but this quotient is actually a homomorphism because we already removed all points in A, so the quotient with respect to A does nothing. But you can equivalently write it like this, because you can quotient, if you consider this as the complement of A and X, you can consider quotient of X with respect to A and quotient of A with respect to A, which is just a point. So this is a complement of a point in this quotient. And this is a complement of this point in this quotient. So essentially, I mean, you can say, for example, X, A. So the quotient just, and you can send the collapsing all A to the point, right? And the complement, here is the complement, so x minus A complement is complement, and here is the complement of this point. But of course, if I remove A here, and I remove point here, this map is actually just homomorphism. And so we know that this is actually isomorphism, since Q since Q restricted on x minus A, so we removed all points from A, so the quotient with respect to A does nothing. So this is a formula. And, okay, so we have these columns, and we also have rows like this. So this is our map F star, which we had before. We showed that this is an isomorphism. So this was appeared in the long exact sequence, and there was a map G star, which appeared in the long exact sequence. So we showed that there is isomorphisms like this. And sorry, this R should be this way. Well, that doesn't matter. And this is here. To construct this map, these maps will be as in excision theorem. And we know that this is isomorphism. So one reaction of the excision was exactly that this is if you there is we excise we have a triple of X subspace inside B, and also there will be A, so we can excise one of those guys to get and the resulting quadratic homology will be isomorphic. And okay, so so this is a commutative diagram, and because the quotients commute with everything here, and therefore, since this is here, these are isomorphisms, and this is isomorphisms, and this is isomorphism, because it's induced by to homomorphism, this means that this might be also isomorphism. Because we can. So all the syrups can be reversed, and they are isomorphism. So we can go like this instead. And this is the isomorphism. Diagram is commutative. And then this the leftmost map is an isomorphism. So x A is the same as x. And this is, and also this is a point. This is this relative. So reduce homology. And so we have immediately the following corollary. So we combine the theorem, which we just proved, and the long exact sequence. For the pair x, comma a. So we assume that this is a good pair. So we learn that there is the following long exact sequence. The sequence so it's convenient to write it in using this reduced homologies. But again, the reduced homologies, they are almost the same as. So for n greater than 0, they're the same as usual homologies. And for n equals 0, they just differ by z. So what we are doing here is, so we had the log exact sequence of relative homology, and in the places we have x comma a, homology of x comma a, this relative homology, we can replace, assuming this pair is good, we can replace it by this quotient. And goes